Okay, stop, reset, run. Oh, no, I made it worse. Killed it. Stop, reset, run. I made it worse. Killed it. Well, at least the Kill the Bit program is working in the raw IMSAI programming environment. Toggle switches only. Alright, I'm testing the flip-flop or latch circuit here on my breadboard. I basically just have this same circuit here. So if the collector of this transistor is pulled low, you know, close to ground by pushing the reset switch, then the output here, the collector of this transistor, should go high, so a low to a high, or forcing this collector high, near 3 volts in this case, through this diode here, should result in this point going low, so the input is opposite from the output. I've got my little circuit here, and currently the scope says the output is low. That's the middle of the screen is 0 volts. So I'm going to take my V plus here. Only to get it to go high, I need to take the input low. So I've got this red wire going to circuit common. I'm going to go to the appropriate diode here, and when I touch it, I should get the opposite state there. Boop, and there it went. Now if I take my orange wire through the other diode, I should get it to go the other direction. And it does. Go the other direction. And back again that way. So that latch circuit works properly. The idea is to take a brief pulse, either from the reset push button or from the output of the QA pin on the shift register, and latch it in, and then use the output to drive the XNOR circuit. The whole point of this is to make sure that the bits are all set off in the shift register at the start of the game. And here I have the oscillator circuit breadboarded. That's this circuit here, and hooked up to my scope. I don't have a trim pot in here at the moment, so I'm just going between the extremes of the 100K speed adjust pot. I've got it to one extreme or the other, so it either has the 2.2K resistor or it has a 2.2 plus a 100K. A 2.2K plus a 100K, one or the other. Right now I just have the 100K here in the circuit. And it's a pretty low frequency, so I get a kind of a jerky looking trace, but I do have the complementary outputs. When one is high, the other is low, and vice versa. So let's see what kind of frequency I have here. I'm in 20 milliseconds per division, and it's 1, 2, 3, 4, 5, 6. So here I have the 100K plus the 2.2K, so that's the full resistance scenario, and I've got my complementary waveforms. I've got 1, 2, 3, 4, 5, 6 divisions at 20 milliseconds per division. So I start out on the calculator here. 20 milliseconds times 6 divisions. Take the reciprocal, and it's about 8 hertz, just a little over 8 hertz. And so now I've taken out the 100K and just have the 2.2K in there. And obviously I'm going to get a much higher frequency signal. So it's 5 milliseconds per division. 1, 2, 3, 4, 5, 6, 7. So 5 at 7. 5 milliseconds times 7. Take the reciprocal, and it's about 28.5 hertz. The signal on the top is representative of the pulse that's going to drive the latch clock input of the shift register, whereas the lower trace should be the one that's going into the shift register clock. And it doesn't really matter. The important point here is that the clocks react to rising edges, so it's really only important how often they come by. Anyway, the oscillator seems to work. The frequencies seem about right, so I don't think any component values need to be adjusted. Alright, there's my circuit board layout as far as the pads and text are concerned. All the text is on the component side, and by convention the pads are all shown on the same side, even though they're on both front and rear sides of the board. Now I've got to put in the traces. Alright, there's the finished circuit board layout in Express PCB's free software. Okay, here are all the parts, well, almost all the parts. I don't have any of the resistors here. I'd ordered a whole new set for the kits I was making from DigiKey, and while they shipped on time, they seem to be in a long-term hold in FedEx for some reason. Each day they kick the delivery date back another day, so I don't know when I'm going to get those. So I'm going to assemble everything except the resistors at this point in time. I have 7 diodes here, 8 LEDs, an IC and IC socket, 5 transistors, a trim pot, 4 of one value of electrolytic capacitor, 1 of another value, a small ceramic axial lead capacitor, 2 tactile push button switches, and a small slide switch. There's the front of the circuit board. Came out pretty good. And the rear of the circuit board. I made some effort in the layout to not have a lot of foils around the display part, other than the kill the bit. I do have this one that's visible. I probably should have gone to extra lengths to hide that one, but oh well. Alright, the IC socket's on, that's the first thing. And the LEDs are on. The diodes. Alright, the 2 jumpers over there in position A. So this board is configured to have the set button at the lower left and the flip button at the lower right. The trim potentiometer for speed adjustment and the 5 transistors are soldered on. The 2 push button switches and the slide switch for power. Alright, the capacitors, both ceramic and electrolytic, aluminum electrolytic, are soldered on. The only thing that really remains are the resistors. Alright, there's the completed board front. And there's the rear side with the two AAA cells installed. Let's see if it works. Looks like the circuit that generates the first pulse works. So obviously the circuit that gives the first bit into the shift register is working. The oscillator or clock is working, and the shift register itself is working. I'm screwing it up and making it worse, but you can see how that works. Okay. Oh, screwed that up big time. Oh, killed it. Killed it even when I had a couple of them going. Now that's at a pretty slow speed. Let's see what happens when I crank the speed up with the pot here. So that's the fastest speed. And this is using the 2.2K resistor right here. Different values can be put in to get different speed ranges. So now there's a nice pokey speed at the lowest end of the pot. Pretty easy to kill at that speed. Anyway, I would say that's a success. Alright, here is my schematic of the Kill the Bit game. I'm not using the one from the version I downloaded, which is a good enough schematic, but I thought that my arrangement of it makes it a little easier to follow the layout of the circuit. So I'm going to give a little bit of a talk here on how the circuit works, dividing it into blocks. Just to reiterate what the circuit concept is, you have a scrolling action driving the 8 LEDs, which are the display of the game. And that's accomplished by an integrated circuit, or IC, which is called U1 in this circuit. That's the component identification number, if you will. It's an 8-bit shift register with latching outputs. There's a lot of shift registers which do not have latching outputs, and the presence of the latching outputs on this particular IC is critical to the functionality of the game. Serial data is presented to the serial input of the shift register, and then it's clocked through the shift register. Each time a clock pulse comes in, the data in the shift register shifts one position through the register, and eventually bits are shifted out of the register at the serial output. And in order to have a continuously scrolling pattern, it's necessary to loop the serial output back into the serial input so that the same bit pattern just recycles through the shift register repeatedly. Because the shift register powers up with presumably nothing in it, just a bunch of zeros, it's necessary to determine when that's the case and force one bit and one bit only into the shift register so that there's a single scrolling LED moving through the pattern. And so there's a circuit that does that. There's also a necessity to have the clock circuit so that the shift register operates. You can't operate the shift register without a clock signal. And finally, there needs to be some means by which to monitor the player's input through the so-called kill switch, and that needs to be compared with the data in the shift register or exiting the shift register so that you can see if a bit was on, and if the player has pushed the button, that then you set that bit to 0. And conversely, if the bit was not on and the player pushes the button, then you have to set the bit. So, and if the player's not pushing a button, you just take the serial data and loop it back unmolested without making any changes to it. So that's a quick overview of what the circuit has. Now here's the power supply circuit. There's not much to it really. You have the battery, and it's 3 volts. Nominally this will be a pair of AAA cells, but it could be other things. There's a power switch that's on the circuit board, and there is a pair of 1 microfarad electrolytic capacitors, one located fairly near the IC and one located over more by the discrete section, so it's got local filtering. And then immediately by the IC is a 0.1 microfarad ceramic capacitor, which is there as a decoupling capacitor. Probably isn't really needed in this circuit because the frequencies are so low and so on, but it's still good practice to put it in. And then finally the IC U1, its VCC pin is tied to the plus 3 volts, and its ground connected to the circuit ground. So that's the whole power supply. And I should note that it's important that the power supply be 3 volts. If it's much lower than that, the CMOS logic won't function. And if it's much higher than that, then you start running into problems with excessive LED current. The shift register IC is not designed necessarily to drive LEDs. However, being a CMOS device, there is some series resistance on all the outputs, which is insignificant in a normal CMOS circuit because the input impedances are so high, but we can make use of that output resistance that's integral to all these outputs and use those as a way to limit the current somewhat to the LEDs that they're driving. However, if you get much of a higher voltage, then the resistances in there are inappropriate to drop the extra voltage, or more importantly, to limit the LED current to a point that, you know, either the LEDs would be too bright or they would be shortened in their life by running a little hot, or possibly even the IC might run too warm and possibly be damaged. So 3 volts is the optimal voltage and really should not be exceeded. So here's an overview of how the shift register works. You can visualize the shift register as being 8 little buckets. Each one can hold 1 bit. And when you apply a clock to the entire shift register, every time there's a clock pulse, everything in the shift register moves down. It gets shifted. If this is the input and this is the output, whatever pattern was in these 8 positions, these 8 buckets, gets moved 1 bucket in this direction. The next time there's a clock, it gets moved 1 more. Next time there's a clock, it gets moved 1 more. Every time the bit in the last bucket gets shifted out, it doesn't just disappear, it gets applied to the serial output of the IC, from where it can be discarded or used in some way. And because there's a vacated bucket, every time data is shifted out of it, there's a serial input, and if you apply just a 0 there, a logic 0, then eventually after 8 clock pulses, the entire shift register will be full of zeros. If you put a logic 1 out here, after 8 serial clock pulses, then the shift register would be full of 1s. If you have some alternating pattern of zeros and ones here, then the shift register will be full of zeros and ones according to that pattern. It's possible through logic to take the serial output and wrap it back around to the serial input, and therefore a bit pattern will just go back around in a loop like this continuously. Or maybe you modify it at some point. Maybe it goes continuously for a while, and then the logic that's looping it back around occasionally makes changes to the bits, and so then you get a modified pattern going around. That's all pretty simple, and that's classic shift register behavior. Now in this particular IC, each of the 8 shift register buckets has an associated latch. So there's 8 latches that are 1 bit each, and the data from each bucket has a corresponding latch. And every time you produce a clock for the latch, it's a separate clock signal into the IC. So every time you get a latch clock, it takes whatever the current bit pattern is here, copies it into the latches, and then after you remove the clock, then this pattern can change, but the snapshot of that pattern is retained in the latches until you give it another clock, in which case it'll update with whatever the current pattern in the shift register is. And then all of these latches have corresponding output pins on the IC, and in this particular circuit, those are connected to LEDs. So if there's a 1 in this first latch, current will go out of the output through the LED and turn the LED on. If there's a 0 in one of these, its associated LED will not have any current and it will be off. So that's the essence of the shift register. So here's the shift register IC again. All pins that are being used are shown except for the VCC and ground, which I've shown in the power supply section. So here we have the serial input. Talked about that in my smaller sketch. That's for data going into the shift register, through the shift register and out. And I've shown the serial output over here on the lower right. But you can still visualize data coming in the serial input, going through the shift register, and exiting on the serial output. Then there's the shift register clear. That's a function I didn't previously describe. It's an active low, so when this is logic 0 or logic low, that's when it clears the shift register. It doesn't care what's in it. When you send the signal in here, it replaces everything in the shift register with a bunch of zeros. And that's used in this circuit to make sure you do start out with a bunch of zeros instead of what may be a possible random pattern. Now here's the serial clock, and every time you have a low to high or a 0 to 1 transition on that, the shift register takes action and shifts everything from one bucket to the next bucket by 1 position. The next time you have a rising edge on the clock, it shifts at another position, and so on. Once the rising edge has happened and the shift has taken place, then the shift register IC does not care what is going on with this. It only cares about the low to high transition. Otherwise, it's not paying attention to this. Now, I mentioned before there's a latch clock. This is also one that acts on a rising edge, low to high, 0 to 1. Every time that happens, that's when it takes the data in the shift register and copies it to the latches. Once that rising edge is complete, then the latch takes no more action until it sees another low to high transition. So the key here is to make this reciprocating scrolling LED pattern is you want to clear the shift register, you want to introduce a single 1 bit into it so it has a single 1 rippling through the pattern, and you want to be able to take the serial output down here and loop it back to the serial input so the pattern goes around in a loop. And every time you've shifted, as soon as that goes away, you want to introduce a pulse on the latch clock so that the current pattern gets copied before it can receive another shift register clock and then change the pattern. So you essentially have an alternate pattern of ons and offs here. When this one gets an on pulse, then this one gets an on pulse, back and forth, and that action moves the shift register, takes a snapshot of it, moves the shift register, takes another snapshot, etc. There's one additional input to the shift register I didn't talk about already, and that's the output enable. All of those 8 latches that are inside the shift register IC, unless you give them permission, they don't actually output a signal. So this is an active low input, so it needs to be tied to ground in order to be active. And it is tied to ground, therefore it is active, and that means that the latches are always outputting signals, either off or an on signal, to the LEDs. So let's look at the clock. This is the clock circuit. It's a classic circuit that uses 2 transistors, 2 capacitors, and essentially 4 resistors. This gets used for all sorts of stuff. It's used as the internal clock in a lot of early digital multimeters. It's used to flash lamps. It's used for all sorts of things. It's an extremely popular circuit. These 2 inner resistors, the values of those, along with the values of the 2 capacitors, determine the frequency of oscillation of this clock, and also how much time does the clock signal spend high and how much time does it spend low. If you have the same values of resistors and the same values of capacitors, then you get a symmetrical or 50% duty cycle wave. If you have dissimilar resistors or dissimilar capacitors, then you may have a pulse that spends just a little bit of time on, then spends some time off, then a brief time on, then a long period off, or vice versa. In this particular situation, one of the 2 resistors, instead of being a fixed resistor, is a 100K potentiometer, along with a small series resistor, which compared to this one isn't very big. It's just so that when you turn this pot all the way down to 0, that you don't end up with a 0 ohm or short circuit here. You want it to keep running, so putting this resistor in here makes sure you can never dial this down to absolutely nothing in terms of resistance. Assuming that this pot is set to roughly its halfway point, that would be 50K. That's really similar to the 47K over here, and with such a small value here, 2.2K compared to the 100K, it's essentially transparent to the speed calculation. So with this pot set to its center, you're going to have a nice symmetrical waveform. But because if you crank it to one side, now you're making half the waveform longer without changing how long the on part of the waveform is, or vice versa. So that affects the speed as well. So not only are you changing the duty cycle, but you're changing the speed of or the frequency of oscillation. Otherwise, it's very simple. The outputs are taken here and here. Only one of these transistors is on at a given point, so when this transistor is on, it pulls this point low, otherwise this resistor is pulling it high. And then when this transistor turns off again, the resistor pulls this point high, and that's when you get a rising edge here going into the latch clock. When this guy goes from transistor on to transistor off, you similarly get a rising edge pulse coming out of here, and that's used as the shift register clock. And because these 2 are alternating back and forth as to whether they're on or off, that's how you get the alternating signals here, which again, only the rising edge going from off to on, or low to high, or 0 to 1, that's the only point in the signal that the IC cares about. So that's how the clock works. Alright, so we have this shift register, and as previously mentioned, we need to first, when we start up the game, when we power it up, we need to make sure the shift register is cleared of all data, so it's all zeros. But a pattern of all zeros is going to look like nothing, so that's no fun. So you immediately, after clearing it, need to put a single 1 into the pattern so that a single bit seems to be scrolling. And so it's necessary to put a 1 into the serial input, and as soon as it's in there, then stop putting a 1 into the 0 input, because you want to put a single 1 and only a single 1 into it initially. So there's this flip-flop circuit up here, and that takes care of that. It's a little crude, and it's not 100%, so sometimes you may have to push a button more than once, but it's a classic power-up circuit, a resistor over a capacitor to ground. So normally the resistor is pulling this point up to a logic high, but on power-up this capacitor needs to charge, so briefly it looks like a short circuit, and therefore it pulls this point low, again for just a second or half a second or whatever. When this goes low initially, when it first goes low, again on a power-up, then this point is pulled low, and here's the shift register clear on the shift register IC, and it's active low. So that low signal here clears the shift register. At the same time this is low, it pulls this point in the flip-flop low through this diode. Now this flip-flop here is similar in many ways to this circuit, and this is a glorified flip-flop with the time delays of the resistors and capacitors added to it. But if you take the resistors and the capacitors off from there and just have the resistors, it operates in the same way except without the time delays, so it doesn't oscillate. It's just flipped one way or it's flipped the other way, so one transistor is always on while the other is off, and vice versa. And when this transistor is off, then this resistor pulls this point up and you get a logic high here. When this transistor is off, then this one must be on, because it's always one or the other. And then when this is on, it pulls this point low against the resistor, and then you've got a logic low. So it flips either way. And you can force the flip-flop by forcing one of the collectors. And that's because the base of each transistor is controlled by the collector of the other transistor. So for example, if I pull this low, then I'm also pulling the base of this transistor low. And it being an NPN transistor, that means that transistor is off. And if this transistor is off, then this is pulling this guy high, and it's trying to pull this base high, which would turn that NPN transistor on, and vice versa. So that's the normal functionality of the flip-flop, but when we have this power on reset, this point is low briefly, and the first action that takes is clearing the shift register. So then this point, still being low, pulls this point low through this diode, and that means the base of this transistor is low, which turns it off. Therefore, the resistor pulls it high, and that high signal goes through this diode, comes down here, and goes into the serial input. Meanwhile, this oscillator is running, so it's sending shift register clock signals into it all the time, and the next shift register clock that comes in after the clear signal has gone away sees a 1 sitting out here on the shift register input, and that gets clocked into the first bucket of the shift register. So now the first bucket of the shift register is a 1. As soon as that happens, well, not as soon, but almost right after it happens, the oscillator gives us the latch clock, and the contents of the shift register are moved into the latches, and therefore the 1 that's in that first shift register position goes through the latch and turns this point to a logic 1. That's confirmation that a 1 has been put into the first position of the shift register. and that comes back around here. By this time the power-up reset is timed out and it's no longer doing anything. So it's like this isn't even there, but we've got this logic 1 coming through here through this diode, and that forces this point high, which through this resistor pulls the base of this transistor high, which turns it on, which now pulls this point low against this resistor, and now this point is low. So it's flipped from being one state to the other, and it's now low. Now the flip-flop will always stay in whatever state it was last forced into until you take action to change it. And there's no more action trying to do anything with this. It's just going to stay in that state where this is now logic low. And since there's a diode here, a low here doesn't propagate through here. It has no effect, and this is just sitting here with this point low, and it's going to stay there until we do something. Therefore, it's no longer putting a 1 here, and the shift register sees nothing happening there. At this point, whatever data goes into the shift register is dependent on this circuit. It takes over once this flip-flop is flipped such that this diode is reverse biased and therefore not influential. So now it's a different path for logic to come in here. Notice that there's a reset push button across this capacitor. Anytime the player wants to reset the game and start over again, usually if he's gotten himself into a position where the LED pattern is too hairy, makes it too hard to play, he can push the reset button. That simulates a power on reset, forces the flip-flop to temporarily go to its other state, which again forces the pattern into the shift register after first clearing it, just like it did on a power-up. So that's what that's doing over there. There's really only one other major part to this circuit, and that's the so-called XNOR circuit, and that's this thing here. It's basically doing the same thing as an IC function. The XNOR, if you drew it using normal logic symbology, like you might if you had an IC that had logic gates in it, this would be the symbol. If you don't put the inversion here and you don't put this extra line here, that would be an OR function. Not NOR, but OR. When you put this extra line on it, that makes it an exclusive OR. And if you put the inversion on the output, that makes it an exclusive NOR, or an XNOR. Here is a table I made up that shows the operation. Being an XNOR, if you just treated it as an XOR without the NOR, then when both inputs are 0, the output 0. When either input is 1, but only one input is 1, then you get a 1 at the output. And if both inputs are 1, then you get a 0 again. So if both inputs are the same state, then you get a 0 output. If only one input is on, then you get a 1 output. Once you make it a NOR, though, now you have to flip that upside down, so the zeros become 1s and vice versa, and this is the pattern you would get. So that's an XNOR truth table. Now, you could put an IC into here to do that, but it doesn't necessarily have all the flexibility we want for this particular circuit. So the original designer of this circuit decided to build it out of discrete components. It has this one transistor here, and the transistor is basically providing the inversion part. It's basically doing the part of this dot. And there are two inputs to the function. One of them is the serial output of the shift register. So whatever data is being clocked out of and shifted out of the shift register, the last bit to fall out of the last position exits the chip on the serial output, and it becomes, I marked it in here as input B. The push button switch, the flip, this is not the same as the reset button, it's the separate button. It's normally pulled high, but when you push the button it pulls it low, so that's the other input to the function, the logic function, and I'm calling it input A here, so that's one input, and this is the other input to the logic function. If you put A and B here, it would be the same thing as what I marked. And the logic itself is being done by the 4 diodes. If you have ones or zeros coming out of here into one of the inputs, and you have a logic 1 over here, because the button is not pushed and this pulls it high. Now that's like this situation where the 1 input is always high, and the other output might be a 0 or the other input, and the other input might be a 0 or a 1, depending whatever's coming out of the serial output. So in that scenario, you're looking at these bottom 2 rows, and the output is a 0 or a 1. If the shift register output is a 0, the XNOR produces a 0. If the serial output is a 1, the XNOR produces a 1. And that's only, again, when you're not pushing the flip button. So that point is logic 1 on the other input. So I'd mentioned earlier that if you just want a scrolling pattern that loops around, you don't want to molest it in any way, you just want to pass the data through. So every time the shift register clocks and a bit, either a 0 or 1, is ejected on the serial output, it goes into the XNOR. It checks to see if the button is pushed or not, and if it is not, it just passes that signal through the XNOR, back around, and it gets brought into the serial input of the shift register and replaces whatever data was shifted out of the first bucket, so now that bit loops around. However, when you do push the flip button, that pulls this low, so now we're into this scenario here. These first 2 rows, when the shift register output is giving us a 0, the XNOR gives us a 1. When the shift register is giving us a 1, the XNOR gives us a 0. So the recycling bit, if the flip button is being pushed, gets flipped to the other logic state. A 0 becomes a 1 becomes a 0. And that's really the essence of how the game works. You've got that scrolling pattern that's already been established. You've primed the shift register with a single 1 in its pattern, and that's going around and around and around. And then if the player pushes the flip button, it gets compared to whatever has just been shifted out of the shift register, which is the same thing as the last output. So when the last output turns on, if that output is on and you push the button at that exact moment, the XNOR will cycle a 0 back into the shift register. So now that bit that was a 1 has been changed to a 0 and is therefore killed. That bit has been killed. And however, if you push the button at the wrong time or for the wrong duration, and now flipping the bit, you could inadvertently set a bit that was off to on, and now you've added 1s to the pattern instead of subtracting 1s from the pattern, and that makes the game more complicated because there's more bits that are on, and it's harder to visually time the pushing of the flip button so that you can kill the bit. In my little schematic here, I made 4 little scenarios for the 4 states that I just described in the truth table, showing what essentially is effective at any given one of the 4 states with the flip input and the serial output. So I kind of explained the way they all work here, but let's just go through it real fast. If flip is 1, and the serial output is 0, the 1 here is trying to turn this transistor on, and the emitter is pulled low, so the transistor is pulling this point low. Therefore, you've turned a 0 to a 0. And remember, when the flip signal is a logic 1, that means the button is not being pressed. So, button not being pressed, a 0 on the serial output gets changed to a 0 at the serial input by that transistor and the surrounding diodes. If the button is not being pushed, so the flip signal is a 1, and you have a 1 on the serial output, now you're trying to turn the transistor on with the 1 at the base, but it can't. The emitter is tied to a logic 1, so it's not actually turned on. The base has to be a higher voltage than the emitter for the transistor to turn on. Therefore, the transistor is off, and the resistor pulls this point high. So that's how we pass a 1 through from the serial output to the serial input. Let's take a situation where the flip button is pushed, so now the flip signal is a 0, and the serial output is a 1. So we're not trying to turn the transistor on from the flip signal. However, the logic 1 here goes through this diode and to the base, thereby trying to turn the transistor on. But because of this diode here, the logic high here can't influence this transistor. However, the flip signal is low, and through this diode here, it pulls the emitter low. So it's almost like the transistor has swapped bases and emitters from the earlier situation. So it's the flip signal that's pulling the emitter low, and the serial output that's pulling the base high. Therefore, the transistor is happy. Its base voltage is higher than its emitter voltage. It turns on, it pulls its collector low against the resistor that's trying to pull it up. Therefore, you have a 0 here. So, with the flip button pushed, a serial output being on turns into a serial input that's off. And the final scenario is, again, the flip button is pushed, so there's a 0 out here. The serial output is a 0, so it's pulling the emitter low, but nothing is attached to the base. There's no base current because due to the diode action, neither the flip nor the serial output is able to control the base. Therefore, the transistor must be off, and therefore the resistor pulls this point up to a logic 1. Therefore, with the flip button pushed, a serial output of 0 gets turned into a serial input of 1.